Again, welcome for this basically meeting today for the lecture. We're going to be meeting at 2:30 today for the lab. So most of the discussion for the lab should be deferred later on. And yes, Heather, there is, I think, a lab PDF file that I already posted. It's a form. So we're going to talk about that and how to proceed about it with the materials that you will need and the steps that you will need to accomplish. The thing with it is, if you miss the lab, you will have difficulty with the lab. So I strongly recommend that you are going to attend the lab. Okay, so you attend it, it's going to be recorded again, and it's going to be posted on YouTube, so that if you miss a step or there is something that you probably was not clear to you, you can go back to the YouTube basically video, go through the steps and make sure you finish the lab accurately and you do it the way it's supposed to be. Now, so that's its own basically discussion forum. If it's still not clear after that, you can still ask questions related to the lab in the discussion for the lab. Let's keep things organized. We should not ask questions related to lecture except in the discussion section for the lecture. We should not ask questions related to the lab except for the discussion for the lab. Now, if neither is working for you because you have an urgent thing, you have a deadline that is coming for your work, and you cannot submit it unless you get an answer to it because it's not clear, you can still ask in the on Canvas on the left-hand side under what is it, messages. You're going to send, or was it send? Wait a minute, let me see exactly how they call it in here. Inbox. I'm sorry, that's the word. You're going to go to the inbox, shoot me a message from there. I should be able to get it in email. Again, when everything else fails, you have two options in terms of emailing me and things like that. Now, it's a good practice, and I already noticed something happening. I don't mean exactly with your class, but at least in several classes I have in my hand, that people tend to start on the assignment late. And then they realize that it's too much work. There is a lot of things to be done. It's a good practice once you have an assignment to start on it right away. Do not leave it to the last day and then realize the amount of work needs to be accomplished. And I will receive a bunch of questions toward the end, basically asking about this and that. And there is repetition also in the questions. And I'm not saying exactly for your class, but I'm saying in general, if you ask the question probably in the discussion forum, and you come back because you want to ask the same question, or somebody asks, I'm sorry, ask the question, and you come to ask a question and you see the question there answered, it saves you time. It saves you time, so you go right away and you start working on your assignment. Now, if you ask a question there, maybe somebody else had this similar question, so again, it benefits the whole classroom. So again, let's keep things organized. First of all, we start on the assignment as soon as possible. We should not delay it. I know some of us are working, some of us have other things, other classes, other projects. But the minute you're free to start on your project, start on it within a day, hopefully. You start on your project, you start on your assignment, you start on your homework. That way, you discover things, especially since we are not online, some of the instructions sometimes is not clear. I mean something and you have a different understanding of it, and then there is a disconnect. And that's going to result negatively on your work. So you start immediately, discover there is a problem, you go to the discussion, reserve it for that specific topic, and you ask a question there. Hopefully somebody has already asked the question, and someone else, not necessarily me, has already answered it, and you save time and you continue working on your stuff. By the time the deadline comes in, you're submitting your work and you're done with it, and you can go free and do other things So that's basically the working thinking that you really have to approach this, not just for this class, but almost for every single class we have in the college. So that's one thing. The other thing I want to emphasize on, there is an assignment due tomorrow for you guys. Do not forget it, okay? It's graded, so don't forget the initial intro that you're supposed to have on yourself, and also the replies to your peers, so that we have that rapport and how to communicate with one another and all of that. So that's one thing. The other thing also is, do not forget the assignments on the homework in terms of Pearson Mastering Physics. So there is already 2 or 3 homework already there, so don't forget those. They should be easy. If you're having difficulty with them, please email me or send me messages. Again, If it's a general question, go ahead and ask it in a discussion related to the chapter. If it's a specific question, please send me messages on Canvas. Okay. So that's in terms of the general thing. We finished chapter 21. Okay. We're starting chapter 22. Unless you guys have another question or something else. No? So let's summarize chapter 21, okay? Imagine yourself for a second that you meet somebody who did not take this chapter, who did not take physics 2 at all, and you tell them, hey, we just finished chapter 21. He or she will ask you, what is chapter 21? What did you learn in chapter 21? So you really should have that idea. You should be able to summarize everything in 2 sentences, 3 sentences at most, everything that you've learned in that chapter, okay? So, remember, in chapter 21, we went all the way back to chapter 4 from the book, namely F equals to ma. And we said we know ma, now the purpose is to find force. People have noticed that charges interact with one another, and Coulomb summarized all of those in terms of a law, which is now we call Coulomb's law. Coulomb's law basically said the following: if 2 charges nailed, fixed, they have to be fixed. If 2 charges interact electrostatically, they will basically attract or repel one another depending on the sign of the charges. If they have similar charges, they will repel. If they have opposite charges, they will repel, they will attract. The force of interaction is proportional to the product of the charges and is inversely proportional to the distance squared. There is a constant there, 1/4 pi epsilon naught, and that is just to make the unit work and things like that. And that depends actually on the medium. Epsilon naught there is the permittivity of the medium. So you have to have that basically in mind. If you put a wall, for example, that separates you between you and the charge, or put a wall between the 2 charges, there will be less force than if they're completely free to interact in space or in vacuum. So that's what that epsilon naught comes into play. And then this force is actually along the 2 charges, between the line, the axis that joins these 2 charges. And again, we've talked about its sign, positive or negative, depending on how the sign of the 2 charges. So that's basically in a nutshell what what the Coulomb's force was. Now we can find the force. We can go back to F equals to ma, solve problems, and we're done. I basically integrate that expression, and we're done with it. However, we defined a new concept, which we said that when we define a new concept, we have to be very careful in. It has to be a physical concept. Physical concept has to be subject to the experiment. And we devised an experiment. I know it's a hypothetical experiment in the sense that you're walking with a Coulomb charge, and you put it anywhere in space and attached to a spring system like this one that measure forces in Newton. And basically whatever the reading on the scale in here is, that is going to be actually the electric field that we defined. Remember, I'm taking 1 Coulomb with me. If I cannot afford 1 Coulomb because we're fresh out of 1 Coulomb, then whatever that number, I have to basically divide by the ratio there. So to bring it back to 1 Coulomb. So if the store says we can give you only 5 Coulombs, that's fine. Whatever the reading on this scale, you divide it by 5. If they tell you, no, we have 1 microcoulomb, so again, you divide it by a millionth, which means you multiply it by a million. So that's basically how the process works for the electric field. It's a physical quantity because you can measure it. And then we decided, you know what, instead of working with the electrostatic force, we're going to be working with the electric field from now on because it's a tangible thing. It's something physical. We can work with it. If we can find it, if we can calculate it, then that's it. Then we can go back and apply F equals to Q times E, where Q is the charge times the electric field, and we're in business. We're back to chapter 4 now. We're 100% basically within our right to go and start working with things. So the new concept is the electric field. So that's how we introduced it. And then we went through a variety of ways basically of how to find the electric field for a point charge, for a line with the distributed charge, which was charge per unit length, and then also on a plane and disk and ring, and did all kinds of things, calculations, and infinite disk, which turned out to be a plane basically. And then between two plates, which we discovered, they have property in a sense that there is no electric field outside between the two plates, but there is a definite value of the electric field between them, provided that the two plates are charged with different distribution charges. One of them is positive and the other one is negative, and it's the same magnitude. Both of them have sigma charge per unit area, but one of them happened to be positive and the other one happened to be negative. That device, which we later on called the conductor, capacitor, we're going to see it far more down the road. I mean, when we do circuits, it traps the electric field because there is no electric field outside between the two sides of the capacitor, either the upper bound or the lower bound, but it's the entire electric field is actually inside of it. So that's means of actually not only measuring the electric field, but you can trap it and walk with it if you like, okay? So that's basically the entire chapter in a nutshell. Okay, so that's chapter 21. Chapter 22, though, is a different approach now to still dealing with the same thing. We're still looking for the electric field. So let me share with you the screen for chapter 22. Do you guys have any questions for chapter 21? Don't forget there is a homework also that is due sometime, I think, next week for chapter 21. That is also printed homework, the one that you turn in by itself and has all of the 6 components that I require on that. Okay, so since you guys don't have any questions, so we're going to move on to chapter 22. So let me share with you the screen. First of all, where am I? Where is share? So again, what is the... So we're going to first of all define what the electric flux is. So that's another concept that we're going to introduce today, the flux of the electric field, okay? And then you will discover later on that it's not as interesting as another flux that we're going to define down the road, which is really the flux of the magnetic field. That's one thing. And the flux is actually a general concept that is introduced way back in the flow of fluids. So fluid dynamics has the concept of flux, and we're going to borrow that concept from there and basically start working with it, and we will have it in our case, and we'll be also actually calculating for different ways and different methods. The purpose of the flux is actually to arrive at Gauss's law. Here is Gauss's law, really, okay, in a nutshell. I put it bolded in here. That is really the goal for today. This is the statement: the total electric flux through a closed surface is equal to that, to the total net electric charge. So add the charges, and then whatever that number is divided by epsilon naught. So here is the deal. If I can find the charges enclosed, okay, so I have 7 coulombs, I have 3 coulombs, I have a -2 coulombs. So remember, it's a net. That means it's an algebraic sum. So whatever is positive has to be canceled by whatever is negative, and at the end, whatever settles, whatever at the end I end up with, that is the net electric charge. Whatever that number divided by epsilon naught. I'm again assuming I'm in vacuum, okay? I'm doing this in vacuum. If I'm not doing this in vacuum, it's going to be different value for the permittivity. Now, from now on, every time we do these things, we're going to assume we're doing it in vacuum or in air, because the permittivity is almost the same. So unless otherwise stated, which is going to be very, very small applications in this entire course, this is basically the assumptions we're going to be going with, that we're doing this in vacuum. So that's the value. That's why you have epsilon naught there. Now, if you can find that ratio, you have found basically the flux of the electric field. That's basically what this thing is. The purpose of the flux actually is an indirect way of finding the electric field. So there are two concepts in here: the electric field by itself and the flux of the electric field. If I know the flux, and this theorem tells me what the flux is, if I know the flux of the electric field, I can reverse engineer this expression and find what the electric field is actually, okay? We're going to use that trying to find the electric field for different configurations. Some of the results we already know. Some of the results we already defined before, and we know them. There will be questions today. So you guys, when you go to the discussion board today, this is not like the first week. You will have questions, so you'll have to take notes basically of the questions and the answers to them. So when you go to the discussion, you're going to see it blank. There is nothing in there, even though people have posted already. When you post, you should be able to see what your answer is and other people's answers are. Now, if you're not happy with your answer because you think it's wrong, because you didn't probably have time to watch the video or attend the class, and you want to edit it and change it, it's not going to mark. So you're going to lose points that way. You're going to lose the whole credit. So my suggestion for you is really watch the videos, okay? The whole thing, because if you do edit the video, it's going to tell me that it was changed. And if you change it, so it's not going to count. So that's basically my advice for you. So please follow through, read the book, try to come back to the class live. I know some of you are working and busy with other things. If you do that, you have to be honest with yourself and actually do the work by going and following the discussion and doing the things that you're supposed to be doing. That's to be honest with yourself more than anybody else. Okay, so we're going to leave the questions for later. So we're going to start this topic, and we're going to start it with where everybody else starts when we're talking about this one, and that is fluid dynamics. I hope that you guys are familiar with the fluids, basically, and how they flow on rivers, for example, and streams and things like that. So that's the analogy we're going to take from there. So let me get my drawing tool in here and see the analogy. Where is my pen here? With fluids. What do you mean? I don't understand. This ones or the ones that I post on Canvas? Oh, this note's in here. Again, I'm going to try to go slow about it, but please try to ask questions right then and there, okay? I think there is a feature in Canvas where you can raise your hand, okay? But try to make sure that everything is clear, okay? No ifs or not ambiguous or anything like that, okay? Okay, so we have, and then in addition, that's the other thing also, when I post this stuff on YouTube, YouTube has these closed captions. I go afterwards and I try to edit them and make them, especially the scientific terms, YouTube misses them big time. So I edit those things for your own convenience, even though probably you don't need closed captions because your hearing is perfect and there is no problem with it or anything like that. But sometimes I myself find the closed captions easier sometimes to follow than the actually spoken words. I have an accent, so sometimes I mess up things big time. And it's a good idea to go and watch those things. I do that all the time myself. And especially if I'm in a busy environment, that's the only thing I rely on. So try to take advantage of that, okay? So here is what the fluid is. I'm not drawing here, why it's not. So imagine with me there is a stream of fluid flowing across a stream, okay? So there is like flow, continuous flow from one side to the other. So I want to know, is it going smooth or is it too strong of a stream, okay? So what I do in this case is I want to measure this quantity, how much flow of liquid, of fluid is going across the stream, the river basically. So this is what I do. I take an area, okay, in here, and basically count how much fluid is passing every single second. So how much fluid passes per second, basically? That's the question. If I can measure that quantity, then I have an idea of the flow. If I measure a lot of fluid, a lot of volume of water, for example, moving around in 1 second, that's a huge flow. That's meaning it's the flux of this fluid is very high. But if I measure, for example, less volume, instead of measuring, for example, this much cubic meters of fluid, let's say, for example, 10,000 cubic meters of fluid going every second, that's a lot of flow. That's a lot of water on this. And I'm going to assume that this is a standard area. It could have been a meter squared for all we care. Standard area, okay? Meter squared, okay? Carry with you a meter squared. Of course, it should not obstruct the fluid, because if it don't obstruct the fluid, so it's useless. Do you guys understand that? It's going to stop it from flowing. So it has to be porous enough for the entire fluid not to be impeded by it. So the fluid is going through, straight through. And my purpose is to find how much flow I'm going to do. Now, if it's not porous, for example, if it's completely empty, it's a solid, so I can actually put it there and wait for it to be full and lift it up and see how long does it take for it to be full. If it takes less time, that means there is a lot of flow. But if it takes a long time for that container to be filled, that means there is the flow is less. So do you guys understand the idea of flow from this perspective? There is two perspectives. I mean, the first one that we're going to go with is the one that take an area and count how much volume of fluid is passing through that area every second. Now, assuming the fluid is moving with the velocity v. So that's the velocity of the fluid. It's moving with v. That means how much volume can I contain in 1 second? So let's extend this space by a v distance. So we go v distance in here. Do you guys agree with me that this is the actual volume of the fluid that I have actually trapped in 1 second? This is v in 1 second is how much fluid passes in 1 second, because it's moving with a velocity v. We're assuming uniform fluid in here, okay? So don't tell me that the velocity may change with time and everything. So we're going to assume that this thing is uniform. That means it's not changing with time. The velocity is not changing with time. So there is a uniform constant flow at the velocity v. So after 1 second, there is the fluid that was here would have traveled in here with a velocity v. Correct or not? Are you guys following me or not? So the volume of the fluid must be the one trapped in that volume, the one that I drew there. Yes or no? And it confirmed. Okay. So basically, at least one of you guys agrees that this is how much fluid has passed in that 1 second. Because I have cross section A and I wait 1 second, that means V volume has already passed through that cross section, and that V times A, that is the actual flow of the fluid that we have in here. Oh man. So the flow in this case is velocity times area. So this is the flow. How much passed by, how much flew on this side, the water that has passed through this cross section, correct? I'm going to do another approach to this same fluid, and you help me on this, okay? I'm going to take the same flow and the same area that I started with, if I can get my pen to write it. So there is another picture now. So the same for the same stream basically that we're looking at, and it's the same area A that we had in the before, except now I'm going to have actually a different tilt to it. Okay. But for me to cover the same flow, so this is A, and this is A, but tilted A. So I'm assuming that this is the same, but in here, it's tilted. So I have to actually get another area now. This is not good enough. You guys see from the geometry, it cannot be the same area. They have the same width, but the height now, since I'm concerned with the same flow, so this is how much flow passed Y by initially, it's V times A. And if I want to trap the same fluid, I have to make the area slightly bigger. If I want to tilt it a little bit. Correct? Because this width must be different than this, I mean, this height must be different than this height. if I'm going to go through the same basically tube where the fluid is passing through, and I'm going to tilt it so that I trap the same amount of fluid that passed through this area will actually pass through the new area now. Is this correct or not? You guys agree with me on this argument? Okay, good. So good. So in order for me to trap the same amount of fluid on the same basically conduit, then I have to really, and I want to tilt the second area, then I really have to have it slightly bigger because it's tilted, unlike the first one, which was straight up, okay? At least from my geometry in here. So the area A prime must be bigger. How bigger it is? How big it is? It's still length times width. And the width is the same, but the length has changed now. Oops, I turned it off. So this is how much length. This is the length of the new length for the area. The first length is L, and the new length is L prime. I'm going to assume that this angle, I'm going to call it the angle phi. I know one of you at least complained earlier about the notes. Do you guys follow the note? At least it's a good idea to try to draw it because I'm going to leave this shape quickly. It's a good idea to follow, at least to have, to imagine where these things are. So I tilted it by an angle phi compared to the initial step, okay? Now the length L prime, and this is the old length, by the way, L, and L prime and L are related through the trig identity. So this is a 90-degree angle, and this is the angle phi. Of course, it's clear from here, from this geometry, that L is equal to L prime times cosine phi. L is the same as L prime times cosine phi, because phi is just the adjacent to that L in this right angle triangle. Does everybody follow me? At least the geometry? Yes. The geometry. Forget about everything else for right now. We're not talking flow or anything like that. I need confirmations. If you're not sure about it, let me know, okay? Okay, at least one of you guys is confirming that it should work. I mean, if I tilt it by an angle phi, and this has to stay the same height basically as before, the new height better be related through this trig identity, namely this is the adjacent in a right angle triangle, and right angle triangle has this identity in it. The adjacent is the hypotenuse times cosine of the angle, which is adjacent to it, okay? Therefore, if I multiply, the width did not change. Both of them, the width is the same. So I'm going to multiply this expression by W, this expression by W. This is the old area. This is now the new area, A prime times cosine of phi. So the old area and the new area are just related by that tilt angle, by the cosine phi that I have tilted with it. Yes? So, if the flow were to be the same, and I defined the flow initially, which I'm going to write it with the capital phi, the letter phi, and like the lowercase phi. So the capital flow then, which was initially AV, is going to be the new flow, which I'm going to replace the value of V by, of A by its new value, which is A prime cosine of phi. So the flow expressed in terms of the area A prime, so it's A prime times V times cosine of phi. All I did in this expression is replace the value of A, that's all. Okay? Because remember, A and A prime are related through this expression. This area A prime is still length times width. It does not change at all. It's still a rectangular shape. That's how they took it to begin with. I didn't take any other shape in here to make life easy on me, so that's a rectangular shape. So the flow in this case is related to that expression. Remember, the velocity is pointing this way, V. What did I do, delta V? I'm sorry. Yeah, no, an arrow. This is V. Okay, it's still pointing in that direction regardless. The area, which you took way back in the physics for A, like this shape in here. Oops, my face is gone. Okay. So the area is a quantity, actually it's a vector quantity, and it's a directed quantity. Depending on the direction with which we flow through the area is actually a vector. That's something that you did way back in physics 4A, and this is the direction. So if I flow the area in the positive direction, namely counterclockwise, that means it's pointing along where the thumb is. So if I wrap my 4 fingers counterclockwise, if I wrap them, the thumb will point to where the area is. So if I flow through this area this way, if I'm moving through the area this way, that means this is the vector area A actually. Okay, the same thing. Let me try to pull a different color now. This for the area. If I go through this area this way, counterclockwise, this is where the area is. It's actually perpendicular to the surface following the right-hand rule, okay? So that's where the area A prime points actually. It doesn't point in the same direction as A. This is where the vector A points. This is where the vector A prime points. So A prime is making an angle with a velocity. So the question then is, what is this angle here? In terms of phi, in terms of the old angle phi. So this is phi, the angle that is made between the 2 basically sides of the areas A and A prime. That is phi. I just defined it as phi. And my question is, what is this angle in terms of phi? How is it related to phi? Does anybody know from geometry? Let me redraw the shapes because now it gets complicated in here. So let me draw these shapes quickly here. If we are in the board in class, so this is the angle phi. Okay. Now this is the perpendicular to this side, and this is the perpendicular to the other side. My question for you guys is, what is this angle? Is it related to phi or not? Is it equal or not to phi?
It's equal.
Okay. And that is because there is a theorem way back that you guys had in geometry, and let me tell you what that theorem is. If I extend the vector v, it's perpendicular to this side of this angle. So these two vectors, these two sides are perpendicular to one another. Now, this is by definition the normal to the area. That's the vector A prime, I'm sorry, is perpendicular to the surface itself. And this is the surface. So these two sides are also perpendicular. This is a 90-degree angle. Since I have two angles whose two sides that sustain them are mutually perpendicular, then in this case, the two angles must be the same. Yes? I mean, there is an easier proof probably if you guys try to prove it differently, and that is using this complements and all of that things from here, from this right angle triangle, which is a 90-degree angle. And if this completes, let me try to think of this. So this is a 90-degree angle, and I'm trying to, and this is a, yeah, I have to extend this side too. Let me get another color in here. Let me get gray. So, and extend this angle, okay? So this side, which is equal to phi, this side, which is equal, I'm sorry, this angle and this angle are equal, and this one plus that one is 90-degree angle, and this one plus this one is also 90-degree angle because this is a right angle triangle. Since this one plus that is 90-degree angle, and this one plus phi is 90-degree angle, this must be phi, which makes it also phi. So there are two proofs for you, okay? Is everybody convinced that's phi or not? Because that's critical, okay? If you guys are not, it's a problem. That is really the whole essence of the problem in here. I want to make sure that everybody is convinced that this angle, that I have a question mark on it in blue, is the same as the tilt angle that I tilted the side with it. Okay? Yes or no? Jaden, you agree? Because I think you put yes in there. I need everybody else to confirm this thing in here because it's critical. And I know you guys did the incline way back. Yes, you guys did the incline also when you were doing physics 4A, and you also dealt with the same argument about the angle of the inclination and how the normal and all of the other things. Okay, very good. So at least I have 2, 3 people now who think that this is correct. So they are the same angle because the two angles actually. Yes, we're going to do that, okay? Okay. Because we just introduced the chapter early. Let me get into this thing in here. So as long as we have this understanding that this side of this angle and the other side also of the other angle are the same, so we're in good shape, okay? So this side and this side are perpendicular to one another, and this side and the other side also is perpendicular to one another, and there is a theorem way back. So if we have that understanding, then we're going to come back to the flux in here and write it simply as the product of this area, which is A prime actually, that's how it is, which is A prime, times the vector V. So this is a vector and that's a vector, and that's the angle between the vector and the area. So this is the actual area itself. So this is the actual area itself, A prime, but it's a vector, and this is the vector V, and they're making an angle between one another, which is phi. So this is reminds you of the dot product, and it's exactly it. So this is actually the flux then is simply the dot product of the area A prime times the vector V. Because all that cosine of phi is nothing but just the angle between them. So we have defined what the flux is. So it doesn't matter what A prime is. Initially, why we had no cosine phi? Because phi was actually 0 degrees. Both the velocity and the area are in the same direction. So cosine of 0 degrees is 1. And that's really what you have to pay attention to here. So when you are talking about an area, it's not the area. This is basically the area, the value of the area. The vector area is actually perpendicular to the area itself. So you have to keep that in mind, because this argument, we're going to need it a lot later on down the road. So I want you to remember that. So the area in this case and the vector V have the same angle. I mean, they are actually parallel to one another. Therefore, cosine of 0 is 1. But in here, they're not. It's clearly V and the area are making this angle of tilt, which is phi, and that's why the flux ended up being this value. So from this point on, we're going to define actually similarly. So this is, I wrote big, it should be big phi actually, I'm sorry. So the flux phi is going to be defined for the electric field similar to how it was defined in the case of the fluid dynamics. For the flux of the electric field, E, and that's what the E index stands for in here, it's going to be actually the vector electric field times the area itself, okay? Provided I have a finite area in here, provided I know what the area is. So that's basically the definition of the flux, okay? That is the definition of the flux. So this is basically how you're going to define it. As long as you can carry with you 1 square meter, and you know how to measure the velocity of the electric field, you're going to be in good shape to find what this flux is. So this flux is a measurable quantity also. So this is something that you can do in the lab. So this is no problem whatsoever. So this is what the flux is. So Newton per Coulomb times meter squared, if you like to use it in SI units, okay? So that's the flux for the electric field from this point on. But however, if the area now is changing, it's not the same, and I have an electric field that is basically going through it, then I have to find a small area, multiply it by the flux, and then integrate throughout the entire area, which is really double integral. So this is really a double integral through the area. So this is the general definition of the electric flux. I know a lot of you probably did not do double. Did you guys do double integrals or not? Multiple integrals, multiple variable integration, or not yet in your case? Did you do that in Calc 2 or not? Or is that Calc 3? Okay, so here is the trick. Okay, very good. Here is the trick. The whole purpose of Gauss's law is so that you don't actually integrate it. So here's the promise, really. This you're not going to be doing in this class. I mean, I know from the get-go you're hit by a double integral, which you didn't cover yet in Calc 3. But the promise is you're not going to be doing this surface integral. This is a surface integral. Okay? The whole purpose of Gauss's law is actually not to do any integration whatsoever. It's the statement is based on the integral, but the actual calculation is not. The actual calculation is going to be basically not that, okay? Not the actual doing the actual integration. Because if all there is to do is the same integral, you will learn that it's not as easy as it's going to be as hard as doing it for the with the first chapter 21, trying to find the electric field the other way, okay? But we're going to do an argument based on symmetry, get rid of the scalar product because this is the scalar product, and we're going to do actually another argument, pull the electric field, make sure that the electric field is constant by symmetry, and then ask ourselves what is the surface of the shape. If we know what the surface of the shape, consult the books. For example, the surface of the sphere is 4 pi r squared. Then just multiply 4 pi r squared times E, and then we actually have not done the actual integral because we just looked at the value of the area of the sphere. Okay. So let's practice calculating the electric field for some specific areas. Okay. So what we have in this example, we have a disk of radius 10 centimeters. This is a 10 centimeter disk, so it's a big disk. It's not a small disk. It's almost this size, okay? No, it's actually probably diameter or radius. Radius, so it's probably bigger than this, okay? Twice this much, so it's about 20 centimeters in diameter. Is oriented with its normal unit vector. So this is the normal unit vector for the area, n. It points toward where the area points, okay? So it depends on the orientation in here. And makes a 30-degree angle. So they gave you the angle in here, 30 degree of magnitude 2.0. So that means just for the how many sig figs to keep in this problem, times 10 to the power 3 newtons per coulomb. Since this isn't a closed surface, we're not talking closed surface. This is an open surface. So that you guys know, in calculus, if you're doing a closed surface, they put a circle in here. Okay, we're not doing that. Okay, we're not doing that yet. We're gonna see that down the road. But for right now, it's an open surface, so just the area has no inside or outside, basically. So this is not like a sphere. A sphere has an inside. A sphere, which is a closed surface, basically limits the space into two regions: an inside space for that sphere and an outside space for the sphere. Okay. Since this is not closed, it doesn't basically determine the difference between inside and outside. So that's why we have specific direction in the figure. So what is the electric flux in this case? Okay. I think some of the homework problems deal with this. So in this case, it's simple. The flux for the electric field in this problem is just E as a vector times A. Okay. The area, you need to find it. The area in magnitude, it's pi times r squared. Okay. And r is given 0.1. So you should be able to find what this, but then you have to have the cosine of, so it's going to be E, which is 2 times 10 to the power 3 in Newton per Coulomb, times the area, which is pi times 0.1 squared. They gave us already the radius, times cosine of 30 degrees. Okay, that's it. That's all there is to it. So you can plug this on a calculator and you should be able to get a value. Don't forget the units. So is this straightforward or not? This is easy. This is so easy that even I can do it. Easy enough? Yep, good. So just plug in numbers, that's all. So this is, if all the class was like this, probably we would not be having issues with it, okay? So this is just straightforward. So the flux through the disk is this much. Now what is the flux through the disk if it turned out so that n is perpendicular to E? Oh, if n is perpendicular to E, that means if the plate, here is the scenario why this question is actually interesting. Let's think of the electric field still pointing this way. The plate now, I'm going to reorient it in such a way it's perpendicular. So here is the plate. Basically, the flow is this way, and you take a disk and you put it in the same direction of the flow. Does it trap any electric field whatsoever? So think of my initial scenario in here and keep on tilting the surface until basically it's going to be like this. It's not going to trap anything. So there is no flux through that surface whatsoever. And that is because in this case, the velocity is this way and the area is that way, and the dot product of these two vectors is clearly 0 because of cosine of 90 degrees. So that's the answer to that question. It's going to be 0 in this case. Because again, E and N are perpendicular. And the area, in this case, the disk would not trap any electric field whatsoever. It would not know that the electric field is there at all. So if that's how you do it, then it's not going to work. So that's really a reiteration of the fact that this is actually a dot product. And to go back to the analogy of fluid mechanics, basically, if you take the area and you try to put it this way, you're not going to trap anything. I mean, if you try to blow on a surface that is this way, and if you are, ignoring Bernoulli's law, which is something else, the surface should not basically be impeded whatsoever. It's going to really ignore that air that is flowing above or below. Of course, there is another problem in here with hydrodynamics, and that has to do with Bernoulli's law, but that's another problem. But not, at least you're not, if you blow it and it this way, it's going to be impacted and it's going to be moving. So what is the flux through the disk if N is parallel? Well, in this case, it's going to be for cosine of 0 degrees. So in this case, N is parallel to E. No, this is not the question yet. That's a good question, Renee. Okay? Okay, so we're going to get to that, okay? And the questions are actually here, okay? So we're going to come down to it and we're going to answer it. The question that is asked is actually here right now, okay? But before we do that, we're going to state Gauss's law, look at this scenario, which will bring us to the question number 1, and then we're going to actually try to prove this law, okay? So here is what the law says, Gauss's law. Now we're considering a closed surface. This is a key word, okay? And like the scenario that we dealt with initially, which was an open surface, this is actually a closed surface. So think of that surface now is actually, you close it, okay, at the end. So it's going to separate the universe into two, separate the space into two regions, a region inside and a region outside. Now, for the region, the total flux now through that surface, that is closed, that's a key word in here, is equal to how many charges are actually enclosed, trapped into that surface, divided by epsilon naught. And this is an algebraic sum, okay? This is an algebraic sum. We did not prove it yet. We're going to prove it quickly. But before I prove it, I'm going to ask you here, does the surface S1 enclose any kind? Remember, this is it looks like these are surfaces. These are not, closed surfaces, I should say. These are not open surfaces. We took a cross cut from here, okay? So you think of the surface of like the basketball, for example, you go with a laser beam and you cut it in half and you're looking at it. But if you do it that way, it's no longer a closed surface, okay? So this is a hypothetical cut. This is a mathematical cut, okay? This is a mathematical representation of what that surface looks like. So this is a closed surface, and my question is, how many charges are enclosed in S1? If you tally. So this is the surface S1. It encloses 0 charges, correct, Renee? So basically, there are no charges in there. Therefore, the flux in this case is 0. So the flux for S1 is 0. Here is S2, and that is the question that you need to answer it later on. So when you're asked in the discussion, you're going to give me the value for S2 and not S1, okay? So S2, how many charges are enclosed in that surface? Divided by epsilon naught, don't forget, okay? 3 charges, but we need to know the sum, the algebraic sum. Remember, that's why I said that you have to really be careful that this is a net electric charge. That means you have to actually add them up. Is it positive or negative for us? You're saying it's positive probably. Okay, but that's not correct. We're missing something, which is the unit.
I don't know how to say that unit.
It's a
like
micro. Okay, let me type the word in here so that you guys are ready to, either you write it micro, and that would be good enough. Okay, I'm sorry, did I put it just to one of you guys? Everyone in the meeting. Okay, so that's how you write this word, micro, okay? That's a microcoulomb, okay? So it's a positive 7 microcoulombs, but that's an incomplete statement. You have to have this divided by epsilon naught. So it's a 7 micro C divided by epsilon. I know it's kind of long. Naught. Okay, that's good enough. Okay, that is an application of Coulomb's law. I mean Gauss's law. So that's a question 1. Okay. Does anybody understand what we're talking about? Does everybody understands what we're saying in here? For example, question for S3. S3, I have a positive 9 microcoulombs, I have a positive 1 microcoulomb, and I have a negative 10 microcoulombs. How much would I have for S3? Zero, yeah. Epsilon naught is just a constant, okay? It's 1 over 4 pi epsilon naught is 9 times 10 to the power 9. It's just property of the vacuum. Okay, does everybody agree with for us? Okay. For S3, that is 0, okay? Good. For S4 now, S4 has a negative 7 microcoulombs and an 8 microcoulomb. Okay, it's a 1 microcoulomb per divided by epsilon naught, okay? Very good. Now, the last area is S5. That means add everything in here, everything. I have, I mean, I could have done it since I know what S4 is. And no, there is a cross section between these things in here. S4 turned out to be, what did you say? 1. S3 is 0. And so S3 cannot be counted. So 1 plus 5, that should be 6 microcoulombs divided by epsilon naught. So that's the entire questions in here. But remember, the question that I am after is for S2 only. Okay. That gives you basically an idea. So let's talk about how this theorem make sense. Okay. Mr. Gauss, who is a very well-known mathematician, he did a lot of things for it, published a paper in 1813, actually, where he suggested this result. He did not have a full proof for it, but he proved it for his case. A lot of people were doing other things there at that time, including some Poisson, I think, and Green, and all kinds of physicists. One of them doing fluid dynamics, heat flow, electricity. He was actually interested in the case of magnetism. That's what he was doing. So that's basically historically the context for it. He did not really prove it in the general case. It was a Russian mathematician actually who did the proof for the whole case. And his name is Ostrogradsky. He did the proof initially in 1826, and then he published the paper in 1831. It turns out that even Mr. Stokes had a theorem, which we're going to need later on down the road in their Ampere's law. And Stokes actually gave it to his students to work on it as part of their exam. And so that's basically historically how these things came about. They're all of the same class of problems, basically, how to convert a problem with triple integrals, for example, into two integrals, or two integrals into a single integral. So that's a mathematical problem. But we're not going to deal with that way at all. We're going to deal with it in simpler than that. So what I'm going to do, I'm going to take a point charge, okay, Q, and I'm going to ask how much flux that Q on a sphere. So I have a sphere in here of radius r, okay? And I want to know how much flux that charge produces just on that sphere, okay? For me, I know what the electric field is for a point charge. We did that from the previous chapter. The electric field, remember, E is going to be simply equal to 1 over 4 pi epsilon naught times Q divided by the distance r squared times r hat, where r hat points in. So this is the point, for example, where this is r hat. Okay? So that's basically what this electric field is. That's what we have seen. So this is E. If I move on a sphere of radius r, well, r squared does not change because it's a radius. It's a sphere. And a sphere of radius r, its radius doesn't change. So the only thing that changes is actually r hat. That's the only thing that changes on a sphere. So what I'm going to do in here, I'm going to take a patch of that sphere and see how much area that sphere has. Patch of sphere is equal to, what is it? Has also direction that is r hat. Again, it's perpendicular to the patch itself. So dA is proportional to r hat. dA on a sphere as a vector. Why did this turn off? As a vector is actually dA itself. So this is a patch of surface. This is not the entire sphere. This is just a patch of that sphere times r hat. Because this r hat, once we move from place to place to place, r hat will change. The patch itself doesn't. So if I'm taking a small quantity of that surface, it doesn't change. But as I'm moving, the actual direction of that surface changes. But so is E also. They both change in the same time. And they stay parallel all the time on this surface. Because of that, and since the flux involves only E times dA, so in this case, it's easy. E times dA, where there is cosine of 0 between them. That's it. Times cosine of 0 degrees, if you like. Okay? Because they are parallel to one another. As long as I calculate them first and I start moving, it doesn't matter which direction I move. Yes, r hat changes for the electric field, and so does it do also for the area too. But their magnitude stays the same as long as I am on the same sphere. Okay? So the idea here is the sphere. This is not a circle, by the way. This is a sphere. So as long as I am on the same sphere, mathematically, it's the same quantity. Now, having said that, then, this flux on the sphere itself, the flux of a point charge, that's the key thing in here. We're starting with a point charge. So this is a point charge Q. We're not saying any kind of distribution. Okay? So for a point charge, it's easy. The flux on a sphere is going to be for the electric field, d phi itself. I'm sorry, let's just take the whole integral, okay, right now. The whole integral of 1 over 4 pi epsilon naught, that is exactly what that field, that times Q divided by r squared times dA. Okay? Remember, we are on sphere. We are integrating on the sphere itself. On a sphere, r does not change. The radius of the sphere does not change. That's basically what sphere is. So I'm going to take everything outside of the integral, and basically I'm left with just the following quantity. Phi for a point charge is going to be 1 over 4 pi epsilon naught times Q divided by r squared, because r is constant, times the integral of a sphere. Basically the area of a sphere, that's all. Times the area of a sphere. When you sum over a sphere, its area, that is the area of a sphere, I'm sorry. Area of sphere. Then I go and look how much the area of a sphere. It turns out to be the area of a sphere is 4 pi r squared. 4 pi times r squared. So I have a 4 pi times r squared divided by 1 over 4 pi epsilon naught times q over r squared. And I have cancellations in here, clearly. I have the 4 pi canceling the 4 pi. That is this number, by the way. And the r squared canceling the r squared. And the flux of a point charge is simply that point charge divided by epsilon naught. So it did it for one point charge. we need to do it for more than 1 point charge to really see if it makes sense to us. Now, if I have more than 1 point charge, and this is a sphere, by the way, before I do anything else, the theorem doesn't say it has to be a sphere. The theorem says that any surface, the total flux of through a closed surface, it didn't say specifically it has to be a sphere. So I have to be careful with that first. And then we'll do the generalization for more than a point charge. Because this is clearly are not spheres. These are surfaces, closed surfaces, okay? So I have to take it now for another shape other than a sphere, okay? So here is the same point charge, Q, but now on a shape that is not necessarily a sphere, okay? And now I'm going to go back to the same issue. I'm going to start somewhere, okay? And that is my patch of surface, if you wish. The area A is pointing this way, or dA, I should say, because this is a patch, not the entire area. And actually, the electric field now is still pointing in the same direction. So I don't have a problem with that. So this is the electric field. Remember, the electric field is always radial. So if I go at this tilted angle, the area is pointing this way, and the electric field is still pointing radial this way. So now I have definitely an area in here. You guys see that? Because the shape now of the area starts to tilt one way or the other, okay? So because of that, this product now is not necessarily the same. But they actually have moved away now. We're no longer on the same sphere. So the electric field also is changing. So this whole integral now becomes a problem. This whole integral now becomes a problem. So we have to analyze that and see what's going on in here. First of all, the electric field has always this r hat component, namely whatever that value, which is 1 over 4 pi epsilon naught times, I'm going to use polar coordinates. Yes, question? Okay, so the picture. The electric field is always radial. It's always in the radial direction, correct? The area now may or may not be in the radial direction, okay? If it was a sphere, it stays in the radial direction. But as I am moving away, now I probably could go like this, okay? Think of this is a random shape. So this is not necessarily in a sphere, okay? So in this case, the area could have a component in the radial direction. So this is r hat still. But this area has a component, when I project it in here along r hat, but has also a component along the perpendicular direction to the r hat, which we call it the azimuthal direction in this case, okay? So far, so good? So I have Q, let me go back to the red pen. So I have Q over r squared. That is the electric field. But the area itself has two components now as a vector. It has a component along the radial direction, and it has also a component along the azimuthal direction, okay? Phi direction, okay? So, I'm sorry, A. Along the azimuthal direction. So it has two components. The area now is a vector that is pointing in whichever way that we're going to take it in this case in here. Okay, it takes in different directions. Now, because this involves a dot product, this product of these two terms is 0 because the perpendicular to r hat is going to be phi hat, and that's going to be 0. So the only component that is going to survive in this case is this component, the radial direction times the direction that is going to be in this case this value in here. And because the area increases with the radius squared, this element in here in the area, I'm sorry, the area will have an r squared in it, and that r squared will be exactly to cancel this r squared. Okay, so in every direction as I am moving up and down, I'm going to actually, so the area in this case is going to be what? 2 times r squared d phi, the angle with which we're going through the area, And at this point, the 2 cancels the 2, and I have the 2 and the phi going from 0 all the way enclosing the charge. So it's going to be another 2 pi that cancels the other 2 pi. But at any given point, as we move away from the charge, the electric field decreases by 1 over r squared, but the area increases by r squared. So they will cancel each other. If I move closer to the charge, the electric field will increase because of r squared now getting smaller, but also the area would decrease by r squared. So the increase and the decrease of the quantities will be mutual, so that the numerator in this case will cancel all the time, even if I have a random shape in here. So the area will cancel all the time, so that the flux of any given surface now, it doesn't matter, it's always going to be q over epsilon naught, regardless of which surface we're calculating this one, regardless of the area, any area will do. Closed area, that is. It has to be closed though, okay? Now that is if we enclose the charge. If we don't enclose the charge, here's the problem. Let's say, for example, I have a charge in here, Q, still point particle, and I have a random area in here, okay? This actually measures the field lines. We should really go back into this expression here, because this is really calculates how many field lines passes through this area, okay? So this is a field line. So if I make the charge bigger and bigger, so the number of field lines that pass through this one in here. So if I calculate this one and trace the field lines, there will be a field line that is coming. So that's going to be a negative contribution in here, because the area is pointing this way and the electric field is pointing that way. And I have another field line in here that is pointing this way in the same direction of this one. So at the end, there will be a net cancellation if I have the charge outside of the area. If you don't believe that, go back to the same analogy that we did earlier, except that now the starting integral, keep the same notation as above, except that the same integral starts with an angle now, doesn't matter which angle, this one angle, for example, and we're going to go back around this surface and come back to the same angle. So the boundaries of integration are not from 0 to 2 pi, but the boundaries of integration from whatever this angle back to it. So the lower bound and the upper bound are going to be the same, and the integral is going to be 0. So this is basically for a point charge, it works fine. For a point charge, the flux of the electric field is equal to the charge that is actually enclosed. It's a point charge that is enclosed divided by epsilon naught. So we did all the cases now basically for it. I'm trying to do the proof without having to actually do a lot of mathematics in this, okay? Now, you ask, what if I have more than a charge? Well, in this case, we are going to invoke the superposition principle. If I have 1 point charge in here and 1 point charge in here, so this is Q1 and this is Q2. So this one will produce its electric field E1, and the other one will produce its electric field E2, and the total electric field is just the sum of the two, E1 plus E2. And since the flux is just the flux of the sum, and the flux is just an integral, so this flux for the sum is going to be the flux that is coming from the charge Q1 plus the flux coming from the charge Q2. The reason being is because when I do the integration for the by definition of the flux, which is a double integral in here, if I can find it. This double integral, I have to treat each charge by itself. I mean, the flux for E1 plus the flux for E2. But the properties of the integral, doesn't matter, single integral, double integral, even triple integral, it's actually a linear operation. That means that this at the end is going to be just the sum of the two fluxes. And each individual charge will give me one Q over epsilon naught, and this one will give me its own Q over epsilon naught. So that's why now it's just the sum of the two Q's over epsilon naught. So this is the flux for 2 point charges. For any number of charges, you just pair them by superposition. Hence the proof for the theorem. Hence the flux of the electric field. Doesn't matter how many charges you have. It's always going to be the sum of all the charges enclosed divided by epsilon naught, by superposition at the end. So you do it for 1 point charge. You argue first of all for the sphere, and then you argue for a non-spherical shape, meaning that any shape, as long as the area is proportional to the radius squared, because now you move away or inward with any shape. But then the electric field also depends on like 1 over r squared. So there is a mutual cancellation in here. So it doesn't matter the distance, at the end you're going to find something that doesn't depend on the radius, which turned out to be Q over epsilon naught. Now you ask, what happened if the charge is outside? The charge is outside, then your starting point of the integral will be the same at your ending. Unlike when you are inside, which starts somewhere, and you're going to do full circle around it, which is going to give you another 2 pi contribution. So you're not going to end up with the same basically point. You're going to end up 2 pi away from it. But if you're outside, you start from this side, and you're going to come back knowing that the other point is away from it. So that's going to go back the starting point. So the integral actually will be the same, lower and upper bound. So the integral from 1 to 1, for example, doesn't matter what the integrand is going to be 0. So at that point, when the charge is outside, there is no contribution to the flux. Now, the last question was, now this is for a point charge. What happened when I have more than a point charge? When I have more than a point charge, basically you just use the superposition again. You just invoke the superposition in your own business. So this is basically the proof for the statement that we're talking about in here. The total flux, the electric flux, through a closed surface is equal to the net electric charge. That means it's the algebraic sum, like we were doing in here, like what we found for S2, for example, being 7 microcoulombs. But don't forget, you have to divide it by epsilon naught, okay? So if you're curious, 7, oh, somebody was asking for the value to see how much it is. So it's 7 times 10 to the negative 6 divided by 4 pi times, or is it 1 over 4 pi? So it has to be multiplied by 4 pi to restore the 4 pi times 9 times 10 to the power 9. So numerically, so there is a number in here, so you're curious about it. So there is a negative 10 to the power 3. It's just a huge number in here, okay? So 9 times 4 pi, which is about 100, times 7, which is about 700,000, roughly, okay? About 700,000 in Newton per Coulomb meter squared, okay? So that's 700,000, okay? So that's what somebody earlier was asking for the number, okay? So that's roughly how much that's going to be, okay? Don't go by this number for the air prompt, just give me 7 microcoulombs divided by epsilon naught, okay? The purpose of which is just to have an understanding that there is a algebraic sum of these quantities. Does this make sense to you guys? Gauss's law, at least conceptually. Yes? No? Okay. At least one of you guys makes sense to him or her. I would recommend, okay, more. I would recommend that you guys really have to review these things. Yeah, I think when I first honestly saw it, I'm just like Jacob, basically, that needed more. Okay, needed more to understand what are we doing in here, okay? So you have to have the following. The first step is in here. The flux of the electric field, when we apply it, it's going to make better sense, okay? The flux of the electric field, which is just the product of the electric field times an area, summed through the entire area, okay? For the case of Gauss's law, it doesn't matter what shape of the area is. That's the thing in here. It's the sum, the algebraic sum of the charges only enclosed. Like, for example, if I go back to the example in here, when we're doing, for example, S2, we consider only the enclosed charge, which are the 9 microcoulombs, the 5 microcoulombs, and negative 7 microcoulombs. We didn't care what this 1 microcoulomb or what this negative 10 microcoulombs or what this 8 microcoulomb were doing, but because they are outside, we don't count them. We only focus on only what is enclosed. For example, for S1, we looked at what is enclosed and we found none to count for. So at that point, we said the flux for S1 is 0. It doesn't matter what the other guys are doing. There are a bunch of them outside. We don't care. We only care about what is enclosed. Now for S3, this turned out to be similar to S1 because when we added them up, as if we don't have anything. So S1 and S3 are identical in terms of their fluxes. They both have 0 fluxes. One of them turned out to have charges inside, and one of them did not. It did not matter because as long as they're 0 of them or they cancel each other. They don't have to be sitting next to one another, by the way. They could be separated by however distance there is, as long as there is that separation between them, okay? Yes? At least conceptually, it should at least start to make sense, but honestly, you have to apply it. You have to really start thinking about it. And the value of Gauss's law, and this is basically how to solve problems with it, and we're going to is the following steps, okay? Let's say, for example, you want to find the electric field for a certain distribution, number one. Of course, you can go back and integrate, do 1 over 4 pi epsilon naught, find the distribution, whatever that is rho, and then integrate through the surface and find your answer, which is one way of doing it. Now, here is another way. If there is a symmetry in your problem, okay? If there is a symmetry in your problem, then you may use Gauss's law. So what you say in this case is, if I can find the charges enclosed, which is not sometimes obvious, okay? Sometimes you might end up doing triple integral here to find what these charges are. Because if the charges are distributed in the space by certain distribution rho, then each element of space, cube of space, has this much charge in it, which is dq, and you have to sum through all of this space to find actually what the actual charge is. I didn't mean phi, I meant q. Okay, q. This is q enclosed. This is a lot, okay? This is actually worse than the first one. So if you end up with triple integral, that means this is not what we are doing at all, okay? Well, some situations there is actually spherical symmetry. In some problems, rho actually doesn't depend on phi and theta, so it depends only on r. So if that's the case, then the element of integration here is just going to be, what is it, 4 pi, for example, if it has spherical symmetry, r squared dr times, so this is dv times rho. And the integral is actually single integral from some lower volume to upper to a certain volume in here. So if this is the spherical distribution here of a charge, so for example, we start from r equal to 0 all the way to up to a certain value. So this depends on space, okay? So this doesn't have a spherical symmetry, okay? But if rho, for example, is on sphere of radius 0 to big R, so this will be my Q enclosed. So if we can do that, we're in business, okay? Rho here may or may not be constant. That's the problem with it. We may have a lot of charge outside and very little inside, or vice versa. Most of the charge is actually inside the sphere. And as we move away, there is less and less charge, or maybe there is a place near the middle somewhere where there is an accumulation of charge. So we have to do this integral, which is a single integral. Now we should be able to do to integrate it, okay, from 0 to r, okay? So there is that problem. So once we find that, then we're going to use the symmetry that I was invoking earlier for the spherical symmetry and say, you know what? This is a sphere. If I have a spherical symmetry, if I have a sphere, as a matter of fact, like this sphere in here, and if I rotate the sphere one way or the other, and you're not paying attention, you would not have noticed that the sphere has been rotated at all if I have a perfect spherical symmetry. So you would not notice that. Therefore, I'm going to take advantage of it, saying that the electric field in here is the same on everywhere else on the sphere. So as long as I am on the sphere, the electric field is the same. Furthermore, it must be perpendicular to the surface itself, meaning it's parallel to the actual area. So the E dot dA becomes E times E dA, which is just scalars with no vectors. And then furthermore, it's constant on the entire sphere. Take it out outside of the sphere and you're in good shape. Now, if I have spherical symmetry. If I don't have spherical symmetry, then I have to take advantage of whatever symmetry. Let's say, for example, I have cylindrical symmetry. If I am on the cylinder, anywhere on the cylinder, I have that symmetry. That means that if I integrate through the symmetry, again, I do the same thing. The electric field probably is the same on the entire surface of the cylinder. So in this case, as long as I stay on the cylinder, the electric field is parallel to the area, because the surface of the cylinder also is perpendicular to the actual surface itself. The area is perpendicular to the surface itself. And E and dA are parallel to one another. And also the electric field is the same. Pull it out, and then you're asking how much is the surface of a cylinder, which you should be able to answer, okay? So you should be able to find what the surface of the cylinder. So this is the cases where we really can use Gauss's law, when there is symmetry. And we argue one way or the other and do that. So let's take a quick example. I know we have another question. So let's first of all introduce conductors, and then we'll take the case of the sphere, okay? Because this chapter is not going to be over today. We're going to finish it next time we meet, okay? And we'll do examples hopefully there. So let's take conductor first. What the definition of a conductor is. Conductor, I mean, we're breaking elements now, materials, into two classifications, conductors and non-conductors. Yes? Yes, thank you. Yeah, because last time we ran out of time and it was not good. Okay, very good. Thank you for reminding me. So let me quickly introduce what a conductor is, okay? So we're dividing materials into conductors and non-conductors, okay? And a conductor, by definition, has free electrons. Electrons ready to move. That's the usefulness of conductors for conducting electricity. If I use a non-conducting material, for example, wood or something, it's useless because it doesn't have free electrons to start to move. Therefore, it's not good conductor. So we have to have, like metals, for example. Metals are usually good conductors. So think of metals as good conductors, and a conductor has that free thing. So if I take a conductor in here, okay, and if I sprinkle charges on it, where would the charges go? Here is the answer to the question. They cannot go inside. Because if these charges go inside, I have a problem. Because if I take an area there around them, if I take an area inside the conductor, I can find what the flux of the electric field is. So the flux of the electric field will be equal to these charges that happen to go inside, the sum over epsilon naught. Since the area is random and it's not zero, so there must be an electric field inside. Okay? And if there is an electric field inside, the charges are free to move. So they will start moving. So they start moving one way or the other, which defeats the purpose that they are there. So they cannot stay there. So there is no charges enclosed inside the conductor. Zero charge enclosed inside a conductor. I mean, if you sprinkle charges, if you charge a conductor, they cannot go inside. Because if they go inside, they will create an electric field because of Gauss's law. And if they do, that electric field will cause the charges to move. Hence, they cannot stay there. So where could they go? All the charges, if you sprinkle charges on a conductor, they must go to the surface only. They cannot go inside. Okay? So that brings me to another question that I'm hoping that you guys also put in there. So what is the value of the electric field inside the conductor? The answer is 0. Okay? What is the first question? It's positive or divided by epsilon naught. You may choose put micro, and you may choose epsilon for the word epsilon naught there. Okay, we still have about a couple of minutes for today, but I'm hoping that, I know we still have a lot to talk about. We still have to apply this thing. We have to actually calculate things with it and find the usefulness of Gauss's law, which is another way of finding the electric field, okay? So the questions again today are the two questions. So hopefully you guys, when you go to later on when the video is posted, you will have a chance to go there and answer the first question and the second question. If you did not have the chance to attend today, or if you know somebody who did not attend today, they must really have to watch these things and go through the exercises that we went through and suffer as we suffered too, basically, so that they can catch these things and grasp these things, because you cannot apply them if you don't have a full understanding of what they are. I mean, Gauss's law, I mean, is not one of the easiest laws in physics. Actually, the entire physics 2 is not the easiest course in physics to begin with. I mean, it involves a lot of things that are more complicated than anything else. We still have about a minute. Any questions before we meet in about 20 minutes? Again, for the lab. Don't forget, there is a different link for the lab. It's not the same link, okay? Last time, I think there were some people who went to this link and they were waiting for us there. Okay, guys, I'll see you in about 20 minutes. Go and have yourself some coffee or water, and then we'll see one another, okay, there. Bye.